Okay, so what is total internal reflection? Hopefully at GCSE you will have covered this and you might have seen this formula before, so we're just going to do a quick recap of GCSE level TIR. So if you shine a beam of light from a ray box into a circular or semicircular block like this, it enters at 90 degrees, so it just passes straight through, and then it leaves the material and we get refraction as we saw in the previous video. And because the light speeds up, then the ray bends away from the normal. So we could look at this in terms of Snell's law. Now, if I increase the angle at some point, well, just increase it a small amount, we get a larger amount of refraction as you'd expect. And then at some point, we get the beam of light refracting along the edge. So the angle of refraction is 90 degrees. That's quite important, as we will see. When this takes place, if I was to measure the angle here, the angle of incidence, that would be the critical angle, and that varies for different materials. And if I increase the angle of incidence beyond the critical angle, then we get TIR. So this surface here, this interface between the perspex, let's say, and the air now acts as a mirror, and we get all of the light reflected. So it's total, all of the light, it's internal, so it's inside the more optically dense material, in this case perspex, and it's obviously reflection. And if I increase the angle beyond that, then I just continue getting reflection. So I is equal to R, the angle of incidence is equal to the angle of reflection. And you may have seen this calculation at GCSE. So the relationship between C and N is as shown here. So if we're given the critical angle is 43 degrees, then I can rearrange this to make N the subject, swap sine C and N is equal to 1 over sine C, and we get 1.47. So this is one way of calculating a value of refractive index by measuring the critical angle. You may be asked for uses of TIR. So there's lots of uses. The main one would be optical fibers and also endoscopes used in keyhole surgery or laparoscopy. So light beams are sent down an optical fiber inside the body, and then the reflected light is carried back up and operations can be done without cutting somebody open, so lots of benefits there. In a more simplistic way, a lot of reflectors and high-vis jackets reflect the light directly back to the source of the light, so it might be the driver of a car, so the headlights are reflected directly back, and they're very, very effective as reflectors. Right, so we have the A-level version of this formula. So sine of theta c, or sine c, that's sine of the critical angle, is equal to the ratio of refractive index, N2 to N1. So N1 is the more optically dense material, N2 is the less optically dense material. So in this case, N1 would refer to perspex and N2 to air, and theta c, as we said, is the critical angle. So we know that the TIR only occurs when the angle of incidence is greater than the critical angle, and the refractive index, or N1, needs to be larger than the refractive index N2. So we're inside the more optically dense material. So we can derive this expression here from the expression we've got for refraction from the previous video. We know at this point here, when I is equal to C, as we said previously, the angle of refraction is 90. So sine of 90 is equal to 1. So we can simplify this expression here. So if we're talking about N1, that's our refractive index. Theta 1 at this case is the critical angle, theta c. N2 is the second refractive index, the second material. And we said that sine theta 2, sine of the angle of refraction, is 1 because it's sine of 90. So we can rearrange this to make sine c the subject, and it's equal to the ratio of N2 to N1. So we can derive this expression with our general version of Snell's law. Right, so let's have a look at a worked example. So we've got an angle of incidence of 65. We have two materials. The first one, a 1.5, and the second one, 1.3 refractive index. So if we were to ask to work out the critical angle, we could just use our new expression. So it's the ratio of N2 to N1. So it's really important to realize that N1 is the first material. So that's 1.5. And N2 is the second material, which is 1.3. And then S sine to the minus 1 will give us 60.1. And very typically in the exam, they'll say sketch what happens to the ray of light. So we know that I is 65 and the critical angle is 60.1. So I is greater than C. So in this case, total internal reflection will occur. So we will get the light reflected back. So the angle of reflection will be equal to the angle of incidence.